special track in the Journal of Signal Processing System from Springer. So if you want to publish something like that, please contact me. I will be very happy to guide you through the submission process. Okay, but this is not the topic of today. Okay, so hello everyone. So I'm Karol Desnos, and I'm going to present you some things that hopefully will be new for most of you. We have heard a lot about AI since Monday, and basically we have heard a lot about deep neural network, a bit of Markov chain, a bit of SVM. We will hear a bit, and we have heard a bit of spiking neural networks. And I want to present you something completely different, which are Tangled program graph, which I believe could be something interesting for hardware friendliness. So yeah, these are my sponsors, let's say. So first of all, is this what Tangled artificial intelligence look like? Unfortunately, no. And for those of you who missed the reference, this is a mix between artificial intelligence and Tangled. So I think most of you who are English speakers and live in an English country probably have recognized it. But unfortunately, this is not what this is about. So what about deep learning? Currently, deep learning is usually as fast as possible and as fat as possible. If we have a look at the hardware and we have a look at what some companies are putting on the market today, we have some companies with huge chips used for training or for inference with several hundred teraflops of computational power. And if we go to the embedded side, then we have some companies that are, okay, with a more reasonable number of giga operations per second. But still, we can see that their goal is to have the most powerful chip possible. And when you see the switch between the old and the new generation, you have a 10-time increase, a bit less, of the computing power. So basically, you want to have the fastest chip possible, even when you are on the embedded side. On the side of deep learning models, and even if we focus on the mobile models, it's kind of the same thing. Basically, if you want to increase the accuracy of your model, you need to have a bigger model. And this is the race that we currently have. Each time we break the record on ImageNet for classification purposes, we have an increase of the number of multiple accumulation operations that we have to do to execute the model. And so what I'm going to present is something that tries to break these cycles by shifting to an entirely new AI algorithm. So what is this algorithm? This algorithm was originally proposed as a reinforcement learning framework. So reinforcement learning is a branch of machine learning in which you have an artificial intelligence that interacts with an environment and tries to learn to do something useful within this environment. So to do that, you have some help. So first of all, your artificial intelligence, which is called a learning agent, will interact with its learning environment, and it will first be able to observe the current state of the environment. Based on this state, the learning agent will be able to act on this environment and to perform some actions to change the state of the environment. The state of the environment may also change thanks to time, physics, or random events that may occur during the processing, or let's say, of the learning environment. As a result of this change of the state of the learning environment, a new state is observed by the learning agent, which will be able to react once again by doing some more actions. So, to learn something useful, you need to have one additional communication channel between the learning environment and the learning agent, and this is the reward. This is basically the learning agent telling the learning environment telling the learning agent whether it is doing something useful or something useless or even hurtful. And so these are the basic principles of the reinforcement learning. And the basic idea is that your learning agent will play with the environment for some time, and it will learn what its useful actions are, what its bad actions are, and in the end, it will have an interesting behavior and a useful behavior. So there are multiple ways to build such a learning agent for reinforcement learning. The most common one is deep learning. Once again, I will not talk about it, but you can perfectly implement such a learning agent using some deep learning techniques. Historically, you can also use some other techniques like Q-learning. And now when we do some deep learning, we basically approximate the Q-learning techniques with deep learning. There are many other ways to do that, and the one I am interested in today are Tangled program graph. So, what are the Tangled program graph? A Tangled program graph, or TPG for short, is an algorithm of artificial intelligence that was proposed originally by Stephen Kelly and Malcolm Haywood from a university in Canada, and that can be represented with a graph. The vertices of the graphs are called the teams. The leaves of the graph, so these are the vertices of the graph that have no outgoing edges. They are called the actions of the graph. And the edges of the graphs are called the programs. So to understand how a TPG works, we first have to dip into what a program is. So let's have a look at what a program is. A program from the outside can be seen as a black box. It receives the state of the environment, the current state of the environment. It does some processing and produces a double value. Don't try to give a meaning to this double value. It has absolutely no meaning. It is not a probability. The only meaning, okay, this one has a meaning, but in general, these double values do not have a meaning. The only meaning they have is compared to other values given by other programs, as we will see later. On the inside, a program is something that looks like an assembly program. You have a sequence of instructions, of simple instructions, and these instructions work on the data that is coming from the environment, so in this example, pixels of a video game. They can also work on results from previous computation. So for example, here, the registers that were set by the first instruction. The result of the last instruction of the program is the result of the program. So this is a very simple assembly-like program. So now, how do these programs work inside the Tangled program graph? So in the Tangled program graph, the leaves of the graph that are called the actions are associated to actions within the environment. So if we are playing a video game, for example, this leaf of the graph is pressing on the button A of my video game controller. And this one is a pressing of button B plus right arrow. Each time I receive a new state of my environment, I will start a new execution of my Tangled program graph. I will start this execution from the root vertex, the root team of my TPG. And what I will do is that I will execute all three programs on the outgoing edges of this team. Each of these programs will produce a value, meaningless values. I compare this value. I identify which is the largest one, and I will follow the path to continue the execution of my TPG. So I will go to this team, execute its outgoing edges, the programs on its outgoing edges, and finally I will reach an action. I perform this action on the environment, I get a new state in result, and I can resume the execution of my Tangled program graph from the root team of my TPG. This is how a TPG works. So pretty simple. So now the question is, how do you reach a TPG structure that is interesting and that does something useful? To do that, we actually use some techniques, some genetic programming techniques, which is a completely different community. And the basic idea of genetic learning is that you start from a population of randomly generated bad learning agents that have a poor score at the video game, let's say. And then you make them play the video games. You identify which are the best one, and you keep them. You identify which are the worst one, and you kill them. You get rid of them. Using the percentage of good solutions that you have, you breed them, and you create some new learning agent by doing some mutation or some crossover operation. And you have a second generation of learning agent. You make them play the video game, you identify the best, you kill the worst, and so on. And eventually, natural selection do its objective, and you will reach, at some point, a population of learning agents that performs well for the tasks you are doing. So how does this translate into my TPG training problem? Basically, when you are training a TPG, you do not have a single root. You have several root teams in your graph. And if you play the video game or if you interact with your learning environment from one of these different root teams, you will have a different behavior. If I play the game from this team, I may follow this path. If I play the game from this team, I will follow a different path and obtain a different score. So what you do is that generation N, you evaluate the performance of each, the fitness of each of these teams. You get a score for each of these root teams. You select the best. You remove the worst one. And then you will create new root teams in your graph. And to do that, you just have to pick a random team in the graph. You duplicate it. So this is what I have done here. I just selected a random team, 2 random teams in the graph, and I duplicated them. I can see that the programs that are referenced by this team are exactly the same programs as the one referenced by these teams. And then I do apply some random mutations. So here, for example, I will randomly mutate the program from this team by swapping some instructions or by changing multiplication and replacing it by an addition, for example. So everything is completely random. Okay, now the question is, how well does it do? Can we actually learn something useful? And of course, if I'm here today, it's because I think we can do something useful with this technique. The first good news is that TPGs are very efficient learner. And what's very interesting about them is that they have an adaptive complexity. If you learn, for example, to play a complex video game, the structure of the TPGs that you obtain at the end will be quite complex. You will have 100 different teams in your program, and so you will have a complex structure. If you try to learn how to play a very simple game, you will have a very, very simple graph with maybe only 10 teams. So the complexity of the learning algorithm adapts itself to the complexity of the game that you are playing. Even better, the data accessed by the learning agent is also adapted to the needs, to its need to perform well in the video game. So if you need to observe the full screen to have a good score, then it will learn that. If you need to observe only a fraction of the pixels of the screen to do your tasks, it will also be able to learn that. And this is, of course, a big advantage compared to deep Q-learning techniques, which have comparable results when you are playing. So these results are based on an evaluation on the arcade learning environment, which is a set of Atari video games, a set of 57 video games. And basically the results of the TPG, the scores that you get with the TPGs in 2017 are similar to the scores that you get with the deep Q-learning techniques at the time. So since then, the deep Q-learning has improved and now they can be better. But at the time, you got the same results, the same average score between TPGs and deep Q-learning. Okay, so they are very efficient learners. The second thing that is very interesting is that they are very fast to execute. On the same architecture, if you do not use the GPU, we were able to have between 3,000 and 11,000 frames per second processed by the TPGs compared to 20 to 1,200 frames per second for the deep Q-learning model. So the amount of computation that you have to do for a TPG is much, much, much lower than the one that you have to do for an equivalent deep Q-learning model. And if you have a range, it's because the games have a different complexity. So if you have a complex game, you probably will be around 3,000 frames per second. The last very, very good news for us in the embedded system community is that the models that you have to store for a trained TPG is very, very, very lightweight. For a trained TPG, the models that you have to store is around 100 kilobytes. And this includes everything, the structure of your graph and the programs on each of the teams on the edge, of the TPG. If we compare that to the equivalent deep Q-learning framework, deep Q-learning model in 2017, we had at least 50 megabytes for the models, and it could go much higher for the most performant deep Q-learning techniques. So these were not my results. Why am I talking to you? Why am I presenting this? It is because since 2.5 years, let's say, we have been implementing this technique in a lightweight way. And the result is the Gelati framework. So Gelati, which stands for Generic Evolvable Graphs for Efficient Learning of Artificial Intelligence, is a library. Oh yes, it was awarded the best paper award in DASIP last year, which was part of HiPEAC. It's a TPG framework that enables you to train, execute, and customize the learning with TPGs, with Tangled Program Graph. It is implemented as a C++ library that is portable and deterministic. It runs on Linux, Windows, and macOS. It is fully documented. We have a very strict constraint on code quality, and of course, it is open source. So you can find it on GitHub and start playing with it if you want to. what are the interesting and original features of Gelati? The first one is that we have some embeddable deterministic parallelism. So as I presented to you, there is a lot of randomness in the training process of TPGs. So we use some pseudo-random number generators, which we can control with a given seed. And if you want to train your algorithm on your laptop or on an embedded chip, you will have the exact same result if you start from the same seed, which is great when you have to debug your system. We also have some parallelism when we try to train on multiple cores. So for example, we did some experiments on Xeon processors with 24 cores, and we got a 21 times speed up compared to a single core execution, which is kind of great for parallel computation. We rarely reach such great speed ups. We have some customizable AI complexity. You can customize the instruction set that you give to your TPG. So the instructions that will be randomly selected to compose the program, you can customize them. And if you want to run on a hardware that does not have fancy exponential, let's say a processor that is able to handle exponential or sigmoid or things like that, you can just use the multiplication, accumulation, and very simple arithmetic. And you can even select the type of data that you want to use. So if you want to go fixed point, you just have to put your fixed point instruction in your instruction set, start your training, and see what results you got. Of course, depending on the instruction set, you may get better or worse results, but you can play with it if you want. The last thing, which is quite new, it's a result that we got during the summer. We also have a way to generate some code for the inference. So in the library, you have a way to train the TPGs, and so we need to manage the graph structures dynamically to add and remove some nodes and to change the program dynamically. But once you get the trained TPG, you can generate an equivalent C code without the graph, with just a simple functions code. And so these are pretty new results which are still unpublished, but basically compared to the single core execution with the graph management, we are able to achieve a speed up between 21 and 40 on a single core. And this was tested on general purpose processors and on ARM processor embedded in a cell phone. So we believe that we can have some very hardware friendly inference with this library. We have a set of applications that are available already on our open source repository. So the Arcade learning environment is available. We have a nice inverted pendulum control. We have done some experiment with the classification on MNIST. We had done some experiment with adversarial games like tic-tac-toe or NIM games. And we are beginning some experiment also on a robotic arm control with preliminary, let's say, good results. Thank you for your attention. I think I'm well within the time. So if you have any questions.